Thus far, we've been talking about techniques designed to test differences either between one sample mean and a population mean, or between two groups, either two different groups or a single group assessed at two different points in time. But what do we do when we have more than two groups? Suppose, for example, we want to compare 3 or 4 treatments all at once. Well, you might think that the best strategy would be to conduct multiple t-tests. For 3 groups, you might suggest we compare the mean of group 1, say with the mean of group 2, then the mean of group 2 with the mean of group 3, and then finally the mean of group 3 with the mean of group 1. Well, for a variety of reasons, this approach won't work. First of all, what would the hypothesis look like? H0 is easy enough, but H1? X bar 1 might be different from X bar 2, but not from X bar 3. X bar 3 might be different from X bar 2, but not different from X bar 1. It's really totally unworkable. Second, the probability of a type 1 error increases with each test. So an approach would be more likely to find a statistically significant result, even if it isn't really there. What we need is a way of comparing all means simultaneously that doesn't actually make use of these means in the calculations. The technique we use is called analysis of variance, or ANOVA. So how does ANOVA work? Well, although the computations are quite different, the idea is the same as it was for t-tests and z-tests. In these kinds of problems, we compared the observed differences in scores with the expected differences in scores by setting up a ratio between the two. We do the same thing with analysis of variance, except that instead of looking at the relationship between observed and expected differences in means, we look at the differences between variances. In any sample, we expect a certain amount of variance. In the case of ANOVA, that variance is called the within groups variance. The ratio shown here compares the variance between the groups with the expected variance, or again, the variance within the groups. The statistic we calculate is called the F ratio. If we see a large amount of variation in each group, then a large amount of variation between the groups won't really surprise us. In that instance, the numerator and denominator will be fairly close to one another, and the F ratio will be small. On the other hand, if we see only a little bit of variation within the groups, but a lot of variation between the groups, then the F ratio will be rather large. As was the case with T and Z statistics, high values in these ratios are associated with a higher chance of rejecting the null hypothesis of no difference between the means. It's really the same thing with the F statistic. Let's take a look at how to calculate F. First, let's remember that we're comparing two variances. What's a variance? Well, as you know from early on in the semester, a variance is simply a sum of squares divided by a value for degrees of freedom for the sample we're looking at. Basically, that's no difference from the variance we compute in a t-test. For a single group t-test, the variance was n-1. For a two-sample t-test, it was n-2. We're not going to worry right now about degrees of freedom for the numerator and denominator in an ANOVA problem. For now, what's important is just to recognize that an F statistic is simply the ratio of two variances. The variance in the numerator, which is the variance between the groups, and the variance in the denominator, which is the variance within the groups. That variance within groups also sometimes is called the error variance, but I'm going to stick with the within groups variance as the terms that I'll use. So solving this problem becomes a matter of computing sum of squares between the groups and the sum of squares within the groups. The easiest way to show you how to compute these values is to work out a problem for you on paper. I've created another video for that, which I'll point you to at the end of this video. For now, let's just jump back and take a look at why ANOVA works the way that it does. This slide shows a simple data set with 7 observations. In this study, the variances within the two groups are quite small. The thing to look at, though, is the sum of squares between and the sum of squares within. We'll get into how to calculate these shortly. Taking into account the degrees of freedom, which we'll also get into in a minute, these values give us an F ratio of 84. Now let's compare this data with data from another study. In this study, the variance within each group is much larger. It's 40.35. Dividing sum of squares between by the sum of squares within, which is of course related to the variance within each group, gives us an F ratio of 1.39. So what's happening here? If we have a relatively large amount of variation within the groups, then variation between the groups shouldn't surprise us. Everything is pretty much all over the place in this situation, and we get a small value for F. A small value for F is less likely to lead us to reject the null hypothesis. Okay, so now we can move on to how to calculate these sums of squares and degrees of freedom. Let's start on the right side of the slide with the calculation for degrees of freedom. We really don't use degrees of freedom total, but if you're interested, it's equal to the sample size n minus 1. Within groups, degrees of freedom is equal to a sample size, again, capital N, minus k, where k is the number of treatment groups. Between groups, degrees of freedom is equal to k minus 1. Calculating the sum of squares within is very straightforward. It's simply the sum of the sums of squares for each group. You'll see how this works in the example problem. But simply put, we just compute the sum of squares for each group in the usual way by adding up the difference between each observation in a group and that group's mean. Now you may be wondering here what the total sum of squares is doing in this equation. After all, if you think back, we don't use the total sum of squares in calculating F. Well, it's there because calculating between sum of squares by hand is rather tedious. So instead of calculating it directly, we calculate total sum of squares and subtract it as shown here. The total sum of squares is calculated by subtracting the mean from all the scores in all the groups taken together from each individual score, squaring the differences and then summing them all up. Again, you'll see how we do this in the next video. But before we wrap up, there's just one more thing I'd like to cover. There are a number of different ANOVA designs. We're going to talk about two of them here, but first a definition of some important terms. Variables in an analysis of variance are called factors. Let's say I'm interested in comparing the GPAs of freshmen, sophomore, juniors, and seniors. The factor in such a study would be class or class level. There are 4 levels for this factor. They are freshmen, sophomores, juniors, and seniors. In this example, we'd use ANOVA to determine whether there are statistically significant differences between these levels, between the means for students in each of the 4 different groups. Now, it's important to note that ANOVA is only able to tell us whether any of the means are different than any of the others. It offers nothing about which means are different. Suppose, for example, that we computed a value for F that was statistically significant. Well, all we'd learn from such a result is that at least one mean is different from the others. In this example, we'd have no way of knowing whether freshmen are different than sophomores, or whether seniors are similar to juniors but different from both freshmen or sophomores, etc. To get at that, we need to conduct what are called post hoc tests. There are a number of different post hoc tests, but we're not going to cover those in this video. Okay. In the last slide about GPA differences between freshmen and sophomores, juniors and seniors, we had a single factor, class, and we had 4 levels of that factor. Designs with a single factor are called one-way ANOVA designs. Suppose we wanted to add another factor, say whether students live on or off campus. In that instance, we'd be looking at differences between on-campus versus off-campus students, and also, at the same time, differences between years, or whether class year and housing status interact in some way. A study with more than one factor is called a factorial design. We can have a number of factors and levels, though if there are more than 3 factors and more than 4 or 5 levels, then analysis of variance gets a bit unwieldy and there are better techniques to use. Okay, let's talk now about the assumptions required for an analysis of variance study. Well, the first is that ANOVA requires interval or ratio dependent variables. things that you can compute means of, obviously. The sizes of the groups need to be roughly equal. The within group variances have to be somewhat similar. And again, very important to remember, ANOVA does not tell you anything about which groups are different. To determine that, again, you need to run post hoc or after the fact tests. So to sum up, ANOVA compares the variation within categories with the variation between the categories. The variation between the categories is known as the mean square between. The variation within the categories is known as the mean square within. If the variation between categories is large relative to the variation within the categories, the value of f will be large, and we reject a null hypothesis that the means of all the groups are equal. As I said earlier, we'll walk through how to calculate these values in the next video. Conceptually speaking, though, I hope that you found this explanation helpful.